everyone, and welcome to the second session of CosmoverseLectures Lectures at Your Desk. CosmoverseLectures Lecture at Your Desk is an exciting new online series that aims to build on the CosmoVerse Training Series and to showcase lecture-style talks on the most prominent works related to cosmological tensions, of course. This will provide earlier stage researchers with an in-depth understanding of the technical details of leading measurements connected with establishing the robustness of the question of cosmic tensions with a real focus on the underlying analysis. I am honored to introduce our today's first speakers. Our first speaker is Dr. Stephen Chen. Dr. Chen is a postdoctoral member at the Institute for Advanced Study. His research interests include building theoretical models for large-scale structure, particularly using techniques from effective field theory and applying these models to constrain fundamental physics using cosmological datasets. As a part of this work, Dr. Chen participated in the year one analysis of the dark energy spectroscopic instrument, which is DESI, of course, including both the measurements of baryon acoustic oscillations, BAOs, and full-shape galaxy clustering. Dr. Chen's today's lecture is titled Large-Scale Structure from Theory to Observables. Dr. Chen, you can start whenever you're ready.
Great, thanks for the introduction. Yeah, so I thought I would talk kind of more broadly about this program of large-scale structure and trying to do physics with it, and so rather than focus on kind of some specific tension. But yeah, I mean, before I start, let me just say that please stop me at any time with questions. I kind of prefer it that way rather than you know, bunch of questions at the end. Yeah, so please stop me whenever, especially if I'm being unclear or if I've said something objectionable, of course. Yeah, so I want to really talk about how we go from the theory to the observables in large-scale structure. So in this kind of introductory slide here, I'm showing kind of a map of all the galaxies that DESI observed as part of his year 3 data release, which is ongoing, and you can see just starting from here that we have this incredibly rich structure, just looking at the distribution of galaxies in the night sky going out at high redshifts. And so the question is, how can we translate this structure that we're seeing, this rich structure that we're seeing, into physics, right? So let's begin with kind of what the observables are, because I think that's kind of a useful place to begin. So I mean, the first thing to say is that our understanding of large-scale structure is fundamentally statistical. This is for many reasons. We perhaps don't particularly care about what the initial conditions are in their specifics other than statistically, but also because our understanding of how this happened through initial quantum fluctuations from, say, inflation, I mean, this is fundamentally a statistical theory. And so we end up wanting to study things like the 2-point function, for example, I'm showing on the left here, which is, what's the excess probability of seeing a galaxy some distance r away, given that there's a galaxy here now, or its Fourier transform the power spectrum, or things like going beyond that, like the 3-point function, which is the excess probability, in addition to that, of having two galaxies at distances r1 and r2 away, given that there's a galaxy here and a galaxy there, and its Fourier transform, which we often call the bispectrum. And what do these things look like specifically? So here I'm showing in a plot, well, in 4 plots really, the 2-point functions in both Fourier and configuration space. So in configuration space, we just call it a 2-point function or correlation function, shown in here in these bottom plots. And in Fourier space, we typically call this the power spectrum, often called P of K. And you can see that these statistics taken here from the Boss survey exhibit a rich phenomenology from which we can learn physics, right? So one thing you immediately notice, for example, is that the correlation function has a peak at about, or a localized feature at about 100 megaparsecs per h. This is what Heejong will talk about in depth, I think, in the next lecture, which is the so-called baryon acoustic oscillation. And you can also see these oscillations in the power spectrum here in the form of this kind of wiggly behavior in Fourier space. Remember, Fourier transform of a wave here turns into a peak. And the other thing you notice, for example, is that these 2-point functions have an anisotropy, so that they not only have a monopole, which is at an angular average, but if you look at angles along the line of sight, there's a bit more clustering or a bit more correlation than there is against the line of sight. So you see that we can measure a monopole quadrupole. In fact, we can also measure higher angular multiples to characterize this anisotropy. And so all these interesting features, which stand out to you even just looking from the plot, can be translated into constraints or on fundamental physics. So how do we do that? Well, since our theories of large-scale structure are statistical, we can in fact write down a likelihood, a so-called likelihood of the theory from the theory of these observed statistics. And often what we do is we use we call it Gaussian likelihood, which is, suppose I measure the power spectrum P of k at, over a number of scales I, then I can write down as a Gaussian a probability distribution comparing what we observed to the data, where this C inverse here is the inverse of the covariance matrix. And just again, as an example, I'm showing here on the upper right corner, the covariance matrix of the power spectrum and the correlation function from the Boss survey. And you can see, of course, some really nice features. For example, in the correlation function here, and its covariance with the power spectrum, you can see that this looks very oscillatory, and this is because these two things are, of course, Fourier transforms of each other. But the thing to emphasize here is that this likelihood function, this probability of the data, given some set of theoretical assumptions or given some set of theoretical parameters theta, is in principle completely specified by the theory. That is to say that this object that I'm writing down here is really a very well motivated form of the likelihood, right? We can really kind of do this kind of calculation from first principles, and we can then combine this likelihood with our priors on the fundamental physics parameters P of theta to write down the posterior distribution that we expect of these fundamental physics parameters given the data. One thing I want to note is that for people who are still getting into the field, we've spent a lot of time developing these models P of theta, say these models of the observables given some set of theory parameters. But of course, as I mentioned, this C inverse itself in principle is also a prediction of the theory, and this theory is far less developed than for the signal itself. And in practice, we usually obtain them from simulations for a variety of reasons. But I think this in the future, really moving towards kind of a more theoretical understanding of the covariance of our various analyses using the same theory that I'll describe in a second, it should be really a fruitful avenue going forward. So let me just say one thing, and I'm really not very much of an observer, really, but I just say that as a caveat, all the things we observe in large-scale structure are not just the thing we observe themselves. For example, the observed galaxies, the distribution of galaxies we see are modulated by foregrounds like dust, which cause extinction in the foreground of the galaxy that is between us and the galaxies, and this often could come from the Milky Way itself. There's extragalactic sources too. And some measurements are quite immune to this. For example, what Hee-jung will talk about in the BAO, but others are not. And so typically what we do is we do a regression or something more fancy between the foreground, for example, here in the extinction, compared to the number of galaxies, and we try to remove via some kind of systematic weight these contaminations. This is a paper from Hee-jung and her student, I think, and you can see just without these corrections, you get humongous changes in the observed correlation function of the galaxies, shown here in the dashed line. I think it's divided by a factor of 5 or something like this. And you really have to be careful on doing these corrections even before you talk anything about what the theory and the fundamental physics analyses part is. And I've focused so far on the spectroscopic galaxy surveys just because it's kind of in some ways it's the easiest picture to talk about. But the picture is very similar for things like photometric galaxy surveys. For example, I'm showing just the projected clustering across the sky of luminous red galaxies from DESI, or for weak lensing surveys. For example, here is the convergence map from DES, or even things like the Lyman alpha forest, which measures clustering through the absorption of quasar spectra. All of these things have very similar considerations. We can measure, again, their statistics. We have theory models for these statistics, like the 2-point function, and of course we typically compute in some theory, at least motivated way, the covariance matrix of these observables. So with all that being said, let me move on and talk about what the theories are. By the way, I don't know if I can see if there are questions and things like this. So I'm guessing the
Yeah, I think somebody asked a question about. So I think
okay.
Harris just asked. If you only can unmute yourself as well to ask a question directly, but they asked what regression is specifically.
Yeah, it's basically I can think of in this picture. I have a bunch of pixels across the sky, and in each pixel I have, say, a number density of galaxies, and I can ask myself, what is the correlation of that number of galaxies with something like this extinction map? So then I can make a plot like this, which shows the trend of the trend of number of galaxies in each pixel with that thing, and since since the fundamental distribution of galaxies should not have this behavior, we can more or less fit a line through it and correct it and correct this trend. And that's kind of what so the simplest version of this is just a linear regression. If that answers the question. Okay. Oh, I guess I can see the chat now.
Yeah, I think we're good.
Great, thanks. Okay, so yeah, so what are the theories? So let me talk about the things that I know a little bit more about. So what are the theories from which we can begin to what is essentially what are essentially these P of thetas that I was mentioning, right? How can we go from a theory of fundamental physics to the observables? And here you heard last week about the CMB, which has its really rich phenomenology. But in contrast, the most difficult part of large-scale structure actually is solving for structure formation in the nonlinear regime. So at early times in the universe, say when the CMB is observed, things are very linear, and even though the physics are very rich, involving all these interactions between dark matter, gas, photons, and neutrinos. For example, I'm showing this video from this paper that Eisenstein, Seo, and White, featuring our next speaker, of course. You can see that we can really solve in a linear regime when fluctuations are very small these dynamics exquisitely, including at late times this kind of gravitational growth of the dark matter fluctuation to form kind of the 2-point function that we were seeing earlier. But in the late universe, where large-scale structural observables sit, fluctuations become very large. They become an order 1 on the scales on which we're interested. So instead, you get something here, like we see here on the right, where instead of some smooth underlying field, we really get huge density contrast, very non-linear looking features, this kind of cosmic web. And for example, here, this 100 megaparsecs per age scale here is roughly the scale at which, for example, we observe the baryon acoustic oscillations feature I was looking at. As you can see, this feature is very subtle, right? It's not obvious to see around one galaxy at all. So how can we surmount this difficulty? How can we go from our basic understanding of things to this? Well, on large enough scales, it turns out that the equation that we're kind of trying to solve for is the so-called Boltzmann equation, which is nothing more than to say that I have some distribution of dark matter or baryons, or I have some distribution of matter on cosmic scales that is a function of the position of what I'm looking at and the momentum I'm looking at, basically the phase space. And the dynamics in this phase space are given by the velocity, so the momentum divided by the mass, on one hand, and in momentum space, the motion is given basically by the gravitational force, which is just the spatial derivative of the gravitational potential. And of course, the gravitational potential itself we can solve by looking at the spatial distribution of galaxies. And this equation and this equation, which holds when we can neglect the physical process of galaxy formation on small scales. Basically, the statement is that on large enough scales, gravity is the dominant force in the universe. This set of equations we can solve in 2 ways, most commonly in 2 ways. The first is using so-called n-body simulations, which solve for it, which basically give us pictures like this on the right. Here, taken from the Millennium simulation. Or we can do things analytically, for example, via perturbation theory. So in perturbation theory, instead of running an expensive but exact solution, we kind of solve for things analytically order by order. And by observing that on large scales we have essentially, even further simplifying from this Boltzmann equation, essentially a gravitational fluid on an expanding background described by general relativity. One thing that I want to emphasize is that we are always implicitly using that we are looking at large enough scales in cosmology. And this is true for both the n-body simulations and perturbation theory. We're always looking at some regime. For example, when we consider gravity-only simulations, we're looking at a regime that are much larger than the kind of influence of the processes of like galactic feedback and star formation. And so I think one thing to really keep in mind as we talk about things is what are the scales of validity of our theories, and what are the scales from which we can robustly model our observables and extract fundamental physics information, right? And beyond this, so I mean, this equation here is really governing the cosmic formation of structure in the total matter distribution. But as we were discussing earlier, what we really usually measure are instead the distributions of galaxies, say, in the universe. And so we need to connect this matter distribution, this complicated matter distribution shown here on the left, to the galaxies, for example, that we observe. And again, here we have two methods, right? The first method is to use simulations where we plant galaxies into these simulated halos, into these collapsed objects, these bright spots in these simulations, and use some empirical model to connect galaxies and halos. This is often called the galaxy-halo connection. And you may have heard of things like the halo occupation distribution, or semi-analytic models, or things like this. On the other hand, which I will talk about more in a second, is there a question? No. Okay. On the other hand, which I'll talk about more in a second, we can also use the same perturbation theory methods we used to describe structure formation earlier from this perspective of gravitational fluid on an expanding background, and extend this effective field theory, which we've built for the formation of structure, to include discrete tracers like galaxies. But in the end, okay, both of these methods are essentially ways to take this kind of nonlinear matter field and plant galaxies onto it, which you can see on the right looks actually quite different from the underlying matter distribution, right? So how to construct this very complicated map is historically one of the very difficult things of studying large-scale structure. So let me just focus on one of these areas, because that's kind of my domain of expertise. So how can we build this kind of effective field theory of galaxy densities in order to plant these galaxies onto the matter field? So historically, this is called historically people in cosmology have often called this the bias expansion, or the galaxy bias expansion. And the logic is actually very simple. That the logic is basically that we take our nonlinear matter field, which we solved for, and we form new fields, or in particle physicsy language, operators, which are allowed by symmetry from the matter field, right? So this means, for example, if you remember from your general relativity class, that local physics cannot depend on things like the net value of the gravitational potential or even the local gravitational force, but really has to depend on the local tidal tensor. And so, for example, we can build these operators from the trace of the tidal tensor, which is just the overdensity of matter. We can square that overdensity. We can form the traceless part of the tidal tensor and square it. This field S squared. And once we build these operators, we just sum these fields up with unknown EFT coefficients, or so-called bias parameters, and get our final galaxy field. So on the right here, I'm showing just kind of a schematic of what this looks like. Right, we have a galaxy density field delta G of X, and this is a sum over all these galaxy bias operators with unknown bias coefficients. Those coefficients, these operators themselves being functionals of the local matter density field. And there's kind of specific terms that are worth pointing out. For example, we can have a so-called counter term, which is basically characterizing the idea that galaxies are not really finite-sized objects at a given point X, but rather have some finite size RH, say, and we have additional terms that are stochastic terms that are coming from the noise of very small scale modes that we've integrated out to produce this effective theory. And we can really think of these bias parameters as encoding the response of the galaxy density, or the response of the formation of galaxies to the presence of long wavelength modes, right? So basically, the picture you should have in mind is that if I zoom out large enough, then I have a response of more galaxies want to form when there's more local overdensities. But this description begins to break down once I zoom in enough that the galaxies look like individual objects with individual sizes rather than as a continuous field. And so this EFT breaks down on either the nonlinear scale or this halo scale RH. And then the modes that are smaller than this, the modes with smaller wavelengths, just contribute a kind of stochastic noise. And this, anyways, this picture is quite complicated in the specifics, but has been the subject of lots of work, starting perhaps with McDonald and Roy in 2009. And the thing to really emphasize, I think, is that this description of galaxy densities are by construction complete up to a given order. That is, if I think that I can get good enough accuracy in my good enough accuracy in my predictions up to some perturbative order, then as long as I've included all the effects up to that order, my description of galaxy densities is complete. I never have to worry about if there are more or less kinds of physics I have to consider. They're all encoded implicitly in these operators and their coefficients. Of course, the flip side of this is that I don't exactly know a priori what these responses are, and so rather than having some perhaps more astrophysical understanding of galaxy densities, I have to go into my data to fit these coefficients. Though, of course, these astrophysical understandings themselves typically come from fitting to data, so perhaps that's not such a big difference. And okay, so let me talk also a bit about what specifically these EFT predictions look like. So one simple picture we can have is what does structure formation look like in a scaling law universe, where the initial conditions just behave according to some power law, k to the n+3, and just as a kind of an example. So this KNL here is basically characterizing the scale at which initial density fluctuations reach order 1, and so here I'm showing for a variety of different redshifts what this quantity k cubed p of k looks like, and you can see that this KNL for different scales corresponds to k of about 0.2 at redshift 0, and way past k of beyond 2 for redshift 2, everywhere in between. And this power law index, which I'm not showing here, is about -1.5, -2 for the scales and redshifts we're interested in. But in any case, we can compute from this. We can compute from these initial conditions the nonlinear corrections from the EFT, and if you compute that for galaxies, it looks something like this. I have a series of loop corrections that look like increasing powers of these initial conditions, n+3. So some number times k to the n+3. This is just linear theory. To the second order, I have this thing squared. The third order, I have this thing cubed. Of course, there are coefficients in front of each of these things that one has to compute. But what you see is we have kind of an increasingly a kind of perturbative expansion that allows us to go to higher and higher k by going to higher powers of this density contrast. In addition to this, the kind of counter term I talked about earlier, for example, produces to leading order a correction that looks like n+3 + 2. Remember, because it looks like k squared. So this is n+5, and then the stochastic term for galaxies starts at k cubed. And the important thing here is that we have a well-behaved expansion in the ratio between k and the nonlinear scale up to KNL. So this theory is well-behaved all the way up to this nonlinear scale, after which the EFT prediction breaks down. Remember, our EFT is again valid only on scales where this gravitational fluid picture of structural formation forms. But before then, we have in principle a very well controlled and converged expansion that tells us how to compute various predictions of structure formation. And just an example here to go beyond the scaling law universe, I'm showing some predictions for my CosmoverseLectures for the galaxy power spectrum. So here in blue, you see the linear theory prediction, and in each of these curves I'm adding on, you can see kind of corrections coming from various kind of terms. So, for example, the loop terms, the stochastic terms, the counter terms, all leading up in green to the final power spectrum prediction for the galaxies. And if people are interested, I'm giving here a link to the notebook that this plot was made from, just to check it out. And you can kind of play around to see which terms come in where, what their various shapes are. Yep. So the natural question you're perhaps asking is, okay, that's given all that mumbo jumbo is, well, does it work? And the answer really is yes. So we've tested over the past several years, up to maybe 10 years even now, the behavior of these models, and you can see, for example, on the left that these models really agree with the predictions from fully nonlinear simulations to the sub-percent, to well below the percent level. And this is true not just for the power spectrum on the left here, but also for the bispectrum. And in DESI, for example, we ran these tests comparing various state-of-the-art codes for predicting these nonlinear clustering to see if we can extract cosmological parameters in an unbiased way. And all these tests have basically come back to show that these predictions from the effective field theory of large structure for galaxy clustering function at well beyond the statistical requirements of both current and upcoming surveys. So okay, with all, I mean that's all a bit of propaganda, but I wanted to just focus on one specific thing. Also because that's going to be the subject of the next lecture a bit. I want to talk about how there actually is a lot of physics hidden beneath the hood for the kinds of things I was just talking about. For example, in the example of the BAO. So if you remember, the BAO is a sharp feature in the 2-point correlation function. Roughly, if I start with the assumption that there's some galaxy here, then there's an enhanced probability out at a radius of about 100 megaparsecs per h that there will be another galaxy there. And so this is a very useful feature because, as Heejun will tell you, we can use this kind of standard ruler, the fact that everything, galaxies will exist between each other at about this distance to measure the expansion of the universe. But there's actually a lot of also interesting phenology in terms of large-scale structure. So one thing that, the first thing that you notice is that the bulk flows that are coherent on scales that are smaller than this ring smear the BAO out. So the random motions, for example, of galaxies as structure forms in a nonlinear way, will tend to blur out the initial feature, going from this kind of sharp initial distribution to something a bit wider. And in lambda CDM, we can show that this effect is big and dominated by long wavelength linear displacements, which kind of damp the initial linear feature in the power spectrum, or the sharp feature in the correlation function exponentially into this kind of form. So we get this very nice theory prediction that these wiggles get damped by e to the minus k squared sigma squared, where sigma squared is defined as this integral over the power spectrum on scales above the BAO scale. And there's been a lot of work going into this. It turned out to input this into our theory predictions requires a process called IR resummation. But what I think is just more important is to say that under the hood, perturbation theory is predicting this effect very well, as you can see in this plot. And the second kind of behavior that is also relevant for the BAO is that galaxies tend to live in overdensities, and overdensities tend to contract under gravity, which means that this ring that we see in the real data tend to be a bit shrunk relative to the real ring you would expect if you were just living at the level of linear theory. And because of Birkhoff's theorem, right? Because of Birkhoff's theorem, it's actually quite straightforward to compute how much shrinking happens, and the shrinking is really just directly related to how much matter is enclosed within this ring statistically. And we can compute, for example, the shift in the BAO in real space, which is given as a function of 1 plus 70 over 47 times the ratio of the quadratic bias parameter over the linear one. And most importantly, this delta squared is again given as an integral, this time weighted by k squared, over the power spectrum, right? So this causes a small effect up to 1% in spectroscopic surveys, which we showed here in DESI, which are small, but of course not small compared to the current statistical precision of current surveys. And as Heejun will tell you, we have ways of getting rid of this, but one thing to note is that, of course, when I fit a full nonlinear model of galaxy clustering, this is implicit in our fits as well. So before I move on, I just want to give some final thoughts on the theory side. So one thing I have not mentioned is the so-called redshift space distortions, which is the fact that observed galaxy positions get Doppler shifted by their peculiar velocities along the line of sight, and this is what causes the anisotropy I was mentioning earlier, causing kind of more higher angular multipoles in the galaxy clustering. And the second more general thing I want to say is that the EFT method is very flexible, and we can formulate it, most usefully perhaps in the presence of new physics. For example, if I have beyond cosmological constant exotic dark energy models, or beyond cold dark matter models, it is in principle very straightforward to add these into the physics that are governing these EFT expansions. And secondly, it is also an interesting task to formulate it for tracers other than matter in galaxies. For example, myself and others, and Misha Ivanov, for example, have worked on how to understand the Lyman alpha forest, which breaks the isotropy along the line of sight of the galaxy bias expansion. We can talk about also of galaxy shapes, which people have worked on, including myself and Zotomir's law, on producing this EFT of galaxy shapes, which is essentially a kind of a spin 2 extension of the normal galaxy bias expansion. We can also talk about how we can deal with the epoch of reionization of the 21 centimeter signal from there. Matt McQuinn has written on this. Basically, the idea is, we have to take into account, the radiative transfer effects from that early time. Because we are simply exhaustively enumerating what the fundamental degrees of freedom are in large-scale structure given theoretical constraints, right? So this is really a way to robustly make sure for each of these observables or for each of these new physics that we are kind of systematically including all the effects that we need to in order to distinguish these between changes in the fundamental physics. I saw that there maybe was a comment, or no, there's not. Okay, good. Yeah, so let me stop here for a second and see if there are any questions or comments. I know I've kind of gone through a lot in the past 20 minutes. Okay.
I don't see any comments in the chats. And
Okay. If not, then I will move on to the kind of the final section of the thing, which is what can we measure and how do we measure it? So what can large-scale structure measure, right? So broadly thinking, I think a kind of a useful way to think about this maybe is that we can think of large-scale structure as constraining shape and growth. And the shape part also implicitly includes geometric information, like from the BAO, which again I encourage you to. Well, of course, you all will listen to Heejung's talk. But for example, on the left here, I'm showing in these plots, how the matter power spectrum being probed by say spectroscopic galaxies changes when I change the matter density. The baryon density, the physical density of baryons in the universe, and you can see that as included. AI induce these wiggly baryon acoustic oscillations, but B, I also cause a suppression of power, which has to do with structure formation during the acoustic era. And on the right here, in this middle panel here, I'm showing instead what happens to structure formation as I increase the matter density. And of course, the first thing you notice is that this peak of in the power spectrum, which characterizes matter radiation equality, shifts to the right as I add more and more matter. And so we can constrain from the observed power spectrum of galaxies all features like this from the shape, right? Just not from the amplitude of the thing, but from the shape of the power spectrum. I can learn many things about fundamental physics, and of course this goes beyond the standard things, but also includes things like neutrinos, early dark energy, things like this. And I can also constrain growth, right? So by tracking how much this curve moves up or down as structure forms. For example, here on the right, I'm showing a plot from a recent paper with Noah Saylor. I can kind of I can constrain how much growth occurs over time and compare it to the prediction of general relativity. Here you can see it being done by cross-correlating CMB lensing with galaxy clustering. I'll talk about this more in a second over cosmic time, and see that it agrees actually quite well with the predictions of lambda CDM and general relativity. But of course, one thing to say is that these two things, shape and growth, are in fact quite tied. So in cold dark matter, the growth of structure is entirely governed by the expansion history. If you write down the equation of motions, you'll see the only thing really entering it are things like a Hubble rate h of z. But for extended models, for example, with neutrinos, this growth becomes scale dependent. And so there's a lot of mixing between the two, right? A change in shape at a given time can be either due to some time-dependent effect of growth, or it can be due to some early universal initial conditions, or some mix between the two. So it's also useful to think, what exactly am I constraining? When I hear about a constraint of the growth of structure, am I thinking, to what extent is this distinguished from a modification of, say, the shape of the power spectrum? And so, I mean, with all that being said, large-scale structure is very good at measuring just how much clustering there is over time. So how much clustering there is over time allows us to measure the growth of structure. And since we have limited time, I thought I'd focus just on probes of growth. Right, so here you can see that here's a table of growth compiled in 2022 from various kind of probes, from weak lensing to galaxy clustering, compared to predictions from lambda CDM from the standard model of cosmology, given the CMB. And historically, there was a tendency for these measurements to be quite low, well, not quite low, but statistically low compared to the predictions from the standard model of cosmology. But not shown in this plot, of course, are a few recent papers showing the opposite. For example, the DESI year 1 results show a clustering from spectroscopic galaxies that is quite compatible with the CMB. There's a recent KIDS legacy paper doing weak lensing with the same effect. So I think this picture may be beginning to change a bit. But what doesn't change, of course, is that there are many probes we can use that are complementary to measure this growth. And how can we do it? Well, as I said, galaxy clustering is governed by a lot of unknown bias coefficients. So how much clustering there is in galaxies doesn't by itself tell us how much growth there is. But typically we can do this by picking out a kind of protected piece of the signal. And what do I mean by this? Well, for example, in the case of spectroscopic galaxy clustering, the redshift-based distortions, which probe again these peculiar velocities and manifest in form of these anisotropies, probe accelerations due to large-scale gravity. And on large scales, since all galaxies fall the same way, we do not have to worry about this anisotropy being from some unknown physics. It really is just probing the gravitational potential on very large scales. And similarly, if I look at how much a galaxy's shape is distorted by weak lensing, this distortion probes the deflection of light due to that same large-scale gravity. And so there's no ambiguity if I measure such a signal, in principle, how much clustering there is. This is kind of a direct, both of these, the velocities in the spectroscopic galaxy clustering and weak lensing, for example, are protected forms of a signal that cannot be confused with extra astrophysics or like galactic feedback or something like this. So let me first talk about the example of spectroscopic surveys. So in linear theory, this is the first time I've written down this equation, I think, in this talk. But in linear theory, for example, we have from Kaiser derived this many years ago that the galaxy power spectrum is equal to b plus f mu squared times the linear matter power spectrum, where mu here is the angle between the wave vector we're looking at, the wave mode we're looking at, and the line of sight. And so the important thing here is that this number f here is the growth rate f of z, which is this universal quantity characterizing the peculiar velocity of galaxies. And so you can see that even though this bias b is galaxy dependent, that is, it depends on which galaxy sample you're looking at, this f is shared between all galaxies. And so by measuring this anisotropy along the angle mu, we can really characterize the extent to which the size of the peculiar velocities. And now there are some caveats I would like to just mention briefly, since I was tasked with talking about what goes into today's analysis of possible systematics might be. And so one example of a systematic, for example, is that if I select galaxies in an alignment-dependent way, like for example, if I select galaxies that are face-on more than if they're edge-on or vice versa, then this assumption here can be broken, because the breaking of this line of sight isotropy in our normal expectation of galaxy formation gets embedded into a new bias parameter that is degenerate with f in our thing. And this was first proposed by Chris Hirata in 2009. To our understanding, this effect should be quite small, but non-zero. So it's very important for galaxy surveys like DESI to characterize how big this effect is. And the second thing I want to say is that there are analogies to this f mu squared term that is protected at higher orders. There's a very nice paper by Fujita and Vaughn in 2020 where they show that kind of this analogy of all galaxies fall under the same gravity can be extended to higher orders using the kind of consistency relations of large-scale structure. But with all that being said, another thing that's very useful to note is that on small scales, this signal gets washed out by nonlinearities. So I'm showing here on the right a fit to the boss galaxies again. And you can see that this linear bias parameter more or less controls the clustering of the monopole, the angular average, whereas this f parameter controls the anisotropy, right, the quadrupole here. And as I go through different amounts of matter clustering, and marginalize over all the other parameters, you can see that no matter how much matter clustering I can put in here, shown here in in these different lines going from less matter clustering to more matter clustering, on small scales going towards higher K, my model is actually able to fit all of these fairly well. And the real distinguishing feature between these analyses with higher and lower matter clustering are really coming from very large scales where the subtleties of galaxy formation, where the nonlinearities from the bias expansion are not setting in. So again, what this is telling you is that there's this protected feature in the power spectrum on very large scales that survives when there are when the nonlinearities are small. So I think this is very useful to know that when somebody tells you, okay, I measured growth from like BOSS or DESI, this growth is really coming from these large scales of K below 0.1 megaparsecs per h, right? I think that's, that what I'll come back to again and again over the next 10 minutes, I guess, is the fact that we really have to be careful about what scales we're talking about in our analyses. So with that being said, let me now talk about measuring the growth of structure using weak lensing. So as I mentioned, weak lensing probes the cosmic matter distributions directly through the deflection of photons from large-scale gravity. So this is just saying that if I look at things like the galaxy shapes or the CMB, the observed distribution of these shapes or the temperature in the CMB will be distorted by the fact that the photons coming to us are kind of curved by the gravity of the intervening matter. So for a source, a galaxy or a CMB at some source ZS, we can write in the limit approximation that the power spectrum of this distortion looks like this. C kappa's kappa on some angular scale L. You can think of L roughly as 1 over theta, where theta is the scale we're looking at, is equal to some integral over the matter power spectrum at a scale. So at each angular scale, some angle theta corresponds to some physical distance and corresponds to some wave number L over chi. And so the thing to take home from all this is that lensing is projected, right? So the angular clustering we're seeing across some angular theta probes things that at very short scales and at very long scales, depending on the distance we're looking at. And so the power at some angular scale is really an integral over the power at physical scales K, where K is this quantity over here. And so this immediately, you're probably thinking, okay, I just made a huge deal about what scales on which I'm measuring the clustering, but now you're telling me that for weak lensing, I'm probing all these different scales, right? So what gives? And why is it interesting, right? So one reason this is interesting, for example, is that this means that weak lensing is very sensitive to small scales, which I told you was kind of difficult to model from gravity-only simulations or from perturbation theory. Right, and so for example, this mixing of physical scales means that weak lensing is sensitive to the scales at which baryonic effects are important. So here, for example, I'm showing a comparison with dark matter only power spectrum measured from a simulation compared to what happens if I include hydrodynamical effects and include effects of galaxy formation. And so you can see as I go to smaller scales for different simulations, they all predict a kind of suppression of power at these small scales that is actually quite hard to model analytically. And these effects actually get imprinted upon the correlation functions of galaxy weak lensing. Here shown, for example, from DES, right? So you can see some of these horizon AGN owls. You can see some of these simulations being imprinted upon these predictions. And so what people usually have to do is to cut out very stringently what angular scales they're using in order to avoid these effects. And remember, this is very different. And remember, this is very different from the case of spectroscopic galaxy clustering I was talking about, where to avoid this effect, I can simply cut off at some scale here, and then I will avoid anything going on smaller scales. Whereas here, I have to cut much more aggressively because my observable is an integral over all these scales. And so I think that's that you're on the one hand, we don't have to worry about how galaxy biasing works. On the other hand, we have to pay a cost over integrating over these scales. But there's one way to get around this, which is to use a cross correlation of weak lensing with galaxy clustering. So when we do cross correlations, when we do cross correlations with a galaxy sample at a well localized redshift, for example, here these different galaxy samples, then I'm localizing the lensing signal I'm cross correlating with at a very well specified distance along the line of sight, which means that again I can restore this translation between the angular and the physical scales. Now I'm showing, for example, in this case, CL, instead of being an integral over all these scales, the CL, the cross correlations are an integral over very well localized, very well confined uh, parts of Fourier space. And I can very cleanly cut, for example, here, if the nonlinear scale is here, I can very cleanly cut my analyses to only include bins that have that depend on clustering up below it. So this is quite different now from the case of pure lensing. Of course, now I have to pay the cost of galaxy bias because this cross correlation naturally brings in the nonlinearities of galaxies. But on the other hand, it's worth noticing, for example, that within the EFT now, which we can now use, the effect of baryons is simply to modify the counter term, this k-squared PFK term, i.e., which is to say that the effect of baryons, even though it is quite mysterious in its full generality, are not mysterious at the large scales that the EFT model. So while I have to pay the cost of introducing new parameters for the effective theory expansion, on the other hand, I gain a very good way to control these systematics that I wasn't able to earlier. And so to finish off this thought, what I think all these examples show us is that different probes of structure formation probe growth at different scales and at different times, right? So here I'm showing this very nice plot made by Kelvin Preston, showing the different scales and epochs being probed by galaxy weak lensing, by CMB lensing, by CMB lensing across galaxies, by spectroscopic clustering. And even though and this is even though we normally summarize in our papers this clustering by one number, say S8, which you might have heard of from lensing experiments. And for future experiments, I think it'll be very useful to go beyond this kind of simple characterization of clustering, right? Whether S8 is in tension between one probe and another, but to really use this kind of full shape information to really distinguish between growth at small and large scales, rather than going to these simple statistics. And of course, if I have a direct model, for example, if I have a model of axion dark matter that suppresses power, in some scale-dependent way, as shown here, I can really directly go, say, in the effective field theory, or even in simulations, from that model to a prediction for lensing power, without ever having to worry about like S8, right? I can really, if I have a specific model in mind, I can translate my constraints directly to a constraint on, say, the axion mass or fraction. And I think that, and I think that will be very, that's one direction that I think will be very promising in the future. And even more than that, well, in addition to that, I should say, in addition to measuring growth beyond one number, I think we can also talk about growth beyond one probe, which, I want to note that all the probes that I've talked about can be combined because, for example, this EFT large scale structure predicts all these things. For example, the redshift space spectroscopic galaxy power spectrum, its 3-point function of bispectrum, its correlation with lensing, all these within one model, right? So particularly, in particular, in the EFT is very straightforward. To simply incorporate more and more observables, all we're simply doing is projecting our theory of large-scale structures onto observables. We do not require any tuning or new extra parameters, essentially, at a fixed order in order to do this, right? We're really just, we're really just doing this very straightforward translation, or maybe not so straightforward translation of theory onto observables. And that's because we have a coherent theory. Well, both in this and in simulations, really, of large-scale structure, and we're just mapping that onto various observables that we're talking about. And I don't know that we have time, so I'll just briefly mention this. There's an additional wrinkle which I think is quite interesting in weak galaxy lensing. Which, remember, weak galaxy lensing is really one of the tightest constraints we can get on matter clustering. And so it's really, continuing to the future, one of the most promising probes of large-scale structure. But it has this additional subtlety that we're measuring galaxy lensing from galaxy shapes. And these shapes are themselves not random because they, in fact, are shaped by the same tidal field that deflects the photons, right? And so, for example, linear order, we can write out the galaxy shape tensor Gij is equal to some coefficient, some linear shape bias CS times the tidal field, local tidal field Sij. And this takes, you can think of this kind of as a modification of the lensing kernel I wrote down earlier to the lensing kernel, to the lensing plus an additional term that's proportional to this linear shape bias at different redshifts. And what this means is that the lensing signal at a given redshift, if we don't know anything about this number CS here and its redshift evolution, we can easily substitute a lensing signal at any given redshift for an intrinsic alignment. And that seems quite problematic. I mean, this is a well-known systematic, again, I think coming to us from Chris Serrata, this is a kind of a very well-known systematic of galaxy weak lensing. And fortunately, of course, these intrinsic alignments are small, and we can model them again within the EFT. And in fact, this is kind of I think this is maybe a future direction of the field. So we can really add them into our predictions on the same footing as the nonlinearities of matter and galaxy densities, right? Remember, I mentioned kind of in passing, I guess, earlier, that we can write on an EFT for galaxy shapes that is simply a spin-2 extension of the thing. You can spin-2, spin-2 you can think of from your quantum mechanics class is just the L equals 2 spherical harmonics. And so here on the right, for example, I'm showing predictions for the galaxy shape clustering for L equals 2 and M equals 0, 1, and 2. You remember this again probably from orbitals and quantum mechanics. And you can see that the EFT is really able to predict this kind of angular structure of the galaxy shape very, very well. And we're really just beginning to learn how to put these predictions into our models for galaxy weak lensing. And I think how to do this robustly and efficiently is an important, outstanding question. But I think there's no doubt that we are now, within the EFT, we are now able to treat all of these different things, on a very secure footing that, is really resting on a very simple set of fundamental assumptions, which is essentially general relativity and a gravitational fluid on large scales. And so with that, let me just conclude by saying, large-scale structure is a land of many contrasts, but it is described by one simple set of rules, right? The EFT, which I focused on here, is one very simple manifestation of this, just because it's kind of simple to explain in terms of equations. But so, in principle, are simulations-based methods, right? We're really talking about having a model of structure formation and then projecting that and the galaxies that we have in it onto a set of observables. A particularly interesting question is where the constraints are coming from, right? What epochs, what time, and what scales, what physical scales. And where that is coming from is set by a combination of the statistical errors on your data and also theoretical errors, right? This marginalization over bias parameters over nonlinearities. And so, for example, when somebody gives you a measurement of the matter clustering S8, you have to be careful in understanding exactly what the number means. Typically, and historically, up to this date, when within lambda CDM, within the standard model, we just report this to one number, but I think it's really worth careful thinking. It's really worth some careful thinking going onwards about what our constraints mean. And, given a particular model to compare, say accident dark matter in this example I showed earlier, we can really measure this change in structure formation, in the growth, in the growth of structure, in the kind of the full shape EFT kind of way, or in the not really just EFT, but in the full shape way of understanding cosmology with no such ambiguity. So anyways, let me stop here and see if there are any questions. Thank you.